Look up at the night sky. Each point of light, each star, is a magnificent fusion engine, but it is also a clock, ticking down. We tend to think of the universe's end as a sudden, cataclysmic event, a final explosion to bookend the Big Bang. But what if the end of everything is not a bang, but an impossibly long, slow, and silent fade to black? The ultimate fate of the cosmos is written not in fire, but in ice. It's a story that unfolds over timescales so vast they defy human comprehension. A future where the very concepts of light, heat, and structure become meaningless memories of a forgotten, vibrant youth. The journey to understanding this final chapter begins not by looking to the future, but by looking back at the single most important discovery about the nature of our universe. It all started in the 1920s with astronomer Edwin Hubble. He pointed his telescope at faint, fuzzy patches of light called nebulae and discovered they were actually entire galaxies, just like our own Milky Way, but incredibly far away. But he found something else, something that fundamentally changed our place in the cosmos. The light from these distant galaxies was stretched or red-shifted, and the farther away a galaxy was, the more its light was red-shifted. The stunning implication was that these galaxies were all flying away from us. But the truly profound insight was that they weren't flying away through space. Space itself was expanding, carrying these galaxies along for the ride. Imagine baking a loaf of raisin bread. As the dough rises, every raisin moves away from every other raisin, not because they are moving through the dough, but because the dough itself is expanding. This discovery was the starting pistol for the cosmic race, revealing a dynamic, evolving universe and raising the ultimate question: does this expansion go on forever? The answer to that question depends on a cosmic tug-of-war between two opposing forces. On one side, you have gravity. It's the force we know best, the cosmic sculptor that pulls matter together to form stars, galaxies, and the grand cosmic web. For most of the 20th century, astronomers assumed gravity was the only major player. The universe was expanding, but gravity was constantly applying the brakes. The big question was whether there was enough matter, enough gravity, to eventually halt the expansion and pull everything back together. But in 1998, observations of distant supernovae revealed a shocking truth. The expansion isn't slowing down, it's accelerating. There's another player in the game, an anti-gravity force pushing everything apart. We call it dark energy, a mysterious, invisible energy that seems to be an intrinsic property of the fabric of space itself. This discovery completely rewrote our understanding of the universe's ultimate fate. Before the discovery of dark energy, a leading theory for the end was the Big Crunch. It's an intuitive and aesthetically pleasing idea. If the universe contained enough matter, then the collective pull of gravity would eventually overcome the outward momentum from the Big Bang. The expansion would slow to a stop, hang for a moment, and then reverse. Galaxies would stop receding and begin rushing toward one another, first slowly, then with catastrophic speed. The universe would heat up as it compressed, tearing apart stars and atoms until everything collapsed back into an infinitely hot, dense singularity, much like the one from which it began. It was a cyclical vision of cosmic death and rebirth. However, with the confirmation of accelerating expansion driven by dark energy, the Big Crunch has been all but ruled out. Gravity, it seems, is losing the cosmic tug-of-war. If gravity isn't going to win, what if its opponent, dark energy, goes completely out of control? This leads to a more speculative and far more violent scenario, known as the Big Rip. This hypothesis imagines a form of phantom dark energy that doesn't just remain constant, but actually grows stronger over time. In this scenario, the accelerating expansion becomes unstoppable. First, in billions of years, the repulsive force would become strong enough to overcome the gravity holding galaxies together in clusters. Then, it would be the turn of individual galaxies like our own Milky Way. Stars would be flung into the ever-expanding darkness. As the end approached, the force would overwhelm the gravity holding solar systems together. Planets would be torn from their stars. Finally, in the last frantic moments, the fabric of space would expand so violently that it would overcome the electromagnetic and nuclear forces, ripping apart planets, stars, and even the atoms themselves. Every fundamental particle would be isolated in an infinitely expanding void. While the Big Rip is a terrifying possibility, the bulk of our current evidence points toward a much quieter, slower, and colder end. This is the scenario known as the heat death, or the Big Freeze. It's not a dramatic event, but an inexorable process dictated by one of the most fundamental laws of physics, the second law of thermodynamics. This law states that in a closed system, entropy, a measure of disorder or randomness, always increases. The universe is like a cup of hot coffee left in a sealed room. At first, there's a useful difference in temperature, but over time, the coffee cools down and the room warms up slightly until they reach the same temperature. At that point of equilibrium, nothing else happens. The energy is still there, but it's so evenly distributed that it can't be used to do anything. This is the future of our universe, a slow, steady slide into maximum entropy and a state of permanent, frozen equilibrium. This process will unfold over timescales that dwarf the current age of the universe. For the next few trillion years, things might seem relatively normal, but the fuel for creating new stars will be running out. The great clouds of cosmic gas and dust will be exhausted. The last small, dim red dwarf stars will slowly form, sipping their hydrogen fuel for trillions of years. But eventually, they too will flicker out. Around 100 trillion years from now, star formation will cease entirely across the cosmos. The stelliferous era, our brilliant age of stars, will be over. The universe will become a graveyard of stellar remnants, cold, dead white dwarfs, neutron stars, and black holes, all orbiting the central supermassive black holes at the hearts of what were once galaxies. Over eons, these galactic structures themselves will dissolve as gravitational interactions fling their dead stars into the intergalactic void. The universe will then enter the degenerate era. It will be a realm of darkness and cold, populated by the degenerate husks of dead stars. But even these remnants are not eternal. Some theories of particle physics predict that protons, a key building block of atomic matter, are unstable and will eventually decay. If this is true, then over timescales of 1036 years or more, all the white dwarfs, neutron stars, and other remaining matter will simply evaporate into a bath of low-energy radiation and particles. After the last proton decays, the only organized objects left in the entire universe will be black holes. This marks the beginning of the black hole era. For an almost imaginable length of time, these cosmic titans will rule the void. But even they are not forever. Thanks to Hawking radiation, black holes slowly lose mass and energy, evaporating over eons until they too disappear in a final flash of particles. After the last and most massive black hole has evaporated, perhaps 10 to the power of 100 years from now, a number so large it's known as a googol, the universe will finally enter its ultimate state, the dark era. It will be a cosmos almost impossible to imagine. The universe will be an unfathomably vast, cold, and dark expanse, perilously close to the absolute zero of temperature. It won't be completely empty, but filled with a diffuse, low-energy soup of photons, neutrinos, electrons, and positrons, all drifting aimlessly through a space that continues to expand forever. In this state of maximum entropy, all meaningful activity will have ceased. There will be no structure, no change, no heat, no life, and no memory of the brilliant, complex cosmos that once was. It will be the final, silent, and eternal equilibrium, the true death of the universe. Faced with this vision of an eventual, eternal void, it's easy to feel a sense of cosmic despair. But perhaps the meaning of our existence isn't found in permanence, but in its precious rarity. The universe, for a brief and glorious springtime, has woken up. We are living in that springtime, in the stelliferous era, a fleeting moment when the cosmos is filled with enough energy and complexity to produce stars, planets, and beings capable of looking up and wondering about it all. The knowledge that this brilliant cosmic age will end doesn't diminish its beauty, it enhances it. The fact that we, a temporary collection of stardust on a tiny planet, can piece together this grand narrative from the Big Bang to the final freeze is the most profound and wondrous thing of all. Our legacy isn't written in the stars, for they too will die. It is written in the understanding we achieve, in our brief, beautiful moment in the sun.